This video is on the properties of definite integrals. And we'll talk about a few different properties. For this first one, we'll start with a theorem, and we'll say for a less than c less than b, if we had this integral from a to b of some function f of x dx, what we can do with this is that since, this is from a is less than c is less than b, so these are x values a and b, c is an x value that falls in between them. We can actually take the integral from a up until c, so the integral from a to c of f of x dx, plus the integral from c onward to b, so plus the integral from c to b of f of x dx. And that's equivalent to the integral from a to b of f of x dx. Basically what it's saying is you're allowed to take the domain that you have, right, the interval that you're taking the integral over, and split it up into smaller sub-intervals and take the integral of each piece. The sum of those integrals is equal to the entire integral over the interval. Let's take a look at an example here. So, for example, if I said find the area under the graph of f of x, and we'll say what f of x is. F of x is equal to, it's going to be a piecewise function. I'll say it's equal to 4 for x less than 2, and I'll say it's equal to x squared for x greater than or equal to 2 on the interval we're going to look at from -4 to 4. So I want to find the area under this graph. Now it might be helpful to sketch it first. To graph this piecewise function, let's talk about what this would look like. I'll draw an x and y axis in here. So we have an x and y axis, and we'll just go 4 away on each of them. Now let's talk about what the graph looks like. The first piece of the graph is really the line y equals 4 for all x values less than 2. So when x is 2, right, the y value there would be up at 4. It's going to be, an open circle. And we'll put another line there so you can see it's 4. And then, right, for x is less than 2, it'll be going this way. Right, so that's that first piece of the function. The second piece of the function for y equals x squared for x greater than or equal to 2, well, what happens at 2? Well, at that endpoint of 2 squared would give you a y value of 4, so it actually ends up filling in my circle, so this function will end up being continuous. And then it follows x squared for all the values, greater than or equal to 2, so we know it's going to have, a type of parabola type shape. Not being 100% accurate, just drawing a sketch of it, but it is a continuous function, right? That hole got filled in. And we want to find the area between -4 and 4. Well, here's -4. Alright, and here's +4. So I'm really looking for this area under the curve here. Right, so that's the area I'm trying to find. And from our previous section, we know that if you take the definite integral of a non-negative curve, meaning a curve that's above the axis, it'll give you the area under the curve. So here, because my function f of x takes on 2 separate values, what I really want to do is I want to take, this and split it, because this is where the function splits. And I want to use a definite integral for this first piece plus a definite integral for the second piece, and that'll give me the entire area under the curve. So in other words, we use the integral from -4 to 4 of f of x dx, which is the entire thing, but we can't actually find it unless we split it up, right? We really need to split it up at this x value, which is at 2. So this is equivalent to the integral from -4 to 2 of the first function f of x, which was 4 dx, right, plus I need the integral from 2 to 4 for how f of x is defined there, which is as x squared dx. And then I'm going to evaluate each of these and then add them together. So the integral here from -4 to 2 for 4 dx, right, which is representing the area that comes from here, the antiderivative of 4 is just 4x. We're going to be evaluating that from -4 to 2. Plus this integral of x squared, remember you add 1 to the power, so x to the third over 3. And we're evaluating that one from 2 to 4. And then we're going to evaluate these individually. Maybe I'll bring this over here so it's easier to see. We sub in, for this first one, we're substituting in 2 first, so you have 4 times 2 minus subbing in -4, so minus 4 times 4. Right, so this is all evaluating this first antiderivative we just found. And then, well, this should be -4 in here, right? So this is minus 4 times x is a -4. So -4 times -4 there. Plus, substituting into here, we're going to substitute the upper limit in first, like we always do. We have 4 to the third power over 3. And then minus, substituting in 2, we'll have 2 to the third power over 3. And we're going to add those together. Well, what do we end up with? We end up with 4 times 2, which gives us 8. -4 times -4 is plus 16, right, because we sub that in there. Plus here, I don't have to distribute anything, so I could drop these brackets here as well. 4 to the third would be 64 over 3, minus 2 to the third would be 8 over 3. And we're going to combine our like terms. They all are like terms. It's easier to add the ones that aren't fractions first. 8 plus 16 is 24. Plus 64 minus 8, so that'll be plus 56 over 3. And then we'll add these together using a common denominator. 24 is the same as 72 over 3, plus we have 56 over 3. So this equals 72 plus 56, which is 128 over 3. Leave that in improper form. Just make sure you know this is in square units or units squared, because we were finding area. We were asked to find area. So make sure you call it square units or units squared. So 128 over 3 square units. The point being is that you had to divide up your domain, right, like we did here, because our function took on different equations depending on which part of the domain you're in. So watch out for that. Make sure you're not just trying to integrate, you know, this first part just using one function or the other. You had to split it up. The next part of this section talks about finding area between two curves. So we'll write out a definition for that and then we'll go through and do it. So if I was looking at this here, we'll write the following theorem and then I'll talk about it. So this theorem says let f and g be continuous. I use CTS for continuous functions. And suppose f of x is greater than or equal to g of x on the interval from a to b. Right, so when I say f of x is greater than or equal to g of x, what I really mean is that the y values that you get here on this interval for f of x are always above the y values for g of x. In other words, this curve would be above this curve. The area of the region bounded by the two curves on the interval from a to b is given by, and the way we talk about it, I'll write this in a second. Let's just talk about how to draw what we're talking about here. So here's an x-axis, here's a y-axis. And suppose I had some sort of function which I'll call f of x. And then suppose there was some other function which I'll call g of x. And I'll label this, where they intersect here is A. I'll label this where they intersect as B. Now they don't have to intersect to do this, but it's helpful to see it. So over this interval, I'm trying to find the area in between the curves. And f of x is greater than or equal to g of x. F of x is the top of this. That's what that's really showing. G of x is really the bottom of this. So to find the area, if I was just looking for the area under f of x, I would take the integral of f of x over a to b, because that would give me the area under the whole thing of f of x. If I was looking just for the area under g of x, this part in here, then I would just take the integral of g of x from a to b, and that would give me that area. So if I want the area in between, what I really do is I take the integral of f of x from a to b, and I'm subtracting off really the integral from of g to x from a to b, because then I'm really saying, okay, f of x would give me all of it. The integral of g of x would give me this part, so if I take all of it minus this part down here, I'm left with what's in between. So the formula we use for this is the integral from a to b of f of x minus g of x dx. And you might want to think of this as f of x is the top curve and g of x is the bottom curve, because that matters. So if they were labeled the opposite way, then g of x would be the top curve and f of x would be the bottom curve, but you would have to always have the top minus the bottom to get the area in between. So, this is how you find the area between two curves. So we should look at an example, and go through it and make sure that we understand how it works. So I'll do that on a new sheet here. So if I said, in this example, find the area of the region bounded by f of x equals 2x plus 1 and g of x equals x squared plus 1. So first thing, you want to make sure you know what these look like. And what you want to do is kind of find where these intersect. So to find the intersection points, if they exist, we can do that by setting the curves setting the curves equal, pardon me. So if you want to set these equal to each other, right, so this is how we're going to find intersection points. You're going to set f of x equal to g of x and then solve for x. So we'll set 2x plus 1 equal to x squared plus 1. And to solve something that's quadratic, remember you want to get 0 on one side and everything else to the other. I'll subtract 2x from each side here. I'll subtract 1, subtract 1. The 1's end up canceling. You end up with 0 equals x squared. These canceled out. Minus 2x. And then how do you solve this? Well, you solve it by factoring. I'm going to factor out x here. So I have x times x minus 2 equals 0. And then solving this, you get x equals 0 and x minus 2 equals 0. Which means adding 2 to each side of this, you get x equals 2. So you have x equals 2 and x equals 0. Now these are the x values where these intersect. You also want to find the y values. So now we find, right, for both of these, find the y values. Well, how do you find the y values? You substitute back into the original functions. And it doesn't really matter which one you pick, because remember, they intersect there. So it should be the same coordinates for the x, for the f of x function as if you sub into the g of x function. So f of 0 would equal 2 times 0 plus 1, which just equals 1. So we know we have the point 0, 1. And then f of 2 equals 2 times 2 plus 1, which equals 5. So I have the point 2, 5. So I know the two graphs intersect at 0, 1 and at 2, 5. And you might want to draw yourself a small sketch. It doesn't have to be anything elaborate, but just enough so you can understand what's going on and which curve is above the other curve. Well, if I was to sketch this out, you know, here's my x and y axis. You should know what they look like. So if I said g of x equals x squared plus 1, we know that's a parabola shifted up 1. So if I have a parabola that's shifted up 1, you know, the origin 0, 0 shifted up, that point that would be at the origin would be shifted up to 0, 1, which you kind of see already as part of our graph. But to draw that parabola, you know, you could just substitute in a couple values. When you had 1 squared, right, subbing into here, 1 squared plus 1, that would be 2, so the point 1, 2 would be on this parabola. When you did 2, 2 squared plus 1 would be 4 plus 1 would give you 5. So you'd be here at 2, 5. And you could draw your parabola in this way, remembering that, you know, it is symmetric. I'm not really worried about this side because I know where these intersect. But so this would be g of x. Right? That's the g of x function. The g of x was equal to x squared plus 1. The other function, f of x equals 2x plus 1, that's a line. It's the line y equals 2x plus 1. Now, you know that we intersect at 0, 1, and 2, 5, so you know these are points on the line. So you could probably just draw it in. But if you weren't sure, the y-intercept would be 1, right? And the slope would tell you to go up 2 over 1, go up 2 over 1, and you'd be on there. So this is, the red line here is f of x equals 2x plus 1. We knew where these intersected. You could have just drawn it in immediately. We're looking for the region that's bounded by these two curves. So I'm really looking for the space in the middle. All right, so I'm looking for that area. Well, how do I find it? Well, you want to take the integral of the top curve minus the bottom curve, because that's how you get the space in between. Well, what's the top curve? The top curve is f of x, right? What function makes up the top area of this region? It's the red one, it's f of x. So we want the integral of the top curve, which is f of x, which would be the 2x plus 1, minus the bottom curve. The bottom curve is the g of x, right? It makes up the lower half of the area, right? The lower region, the lower boundary. So that's minus x squared plus 1 dx. Now what's the integral over? Well, where are the intersection points? The x value of 0 to 2. We found them here. You could also see it starts at 0 to 2. Now it doesn't always have to have an intersection point. They might just tell you which points to do it from, and then you would. Notice how we're doing this though. This is, I said it out loud, but this is the top curve, right? This one here is the bottom curve. So it's always the top minus the bottom when you're doing this. So don't think it always has to be called f of x and g of x. They might be labeled the opposite way. They might just both be labeled y. You have to know it's the top minus the bottom. Now once you have that, now we're ready to take that antiderivative. And you might be better off simplifying the inside before integrating, just because it'll be easier to work with. So if I just simplify the inside, the integral from 0 to 2, I'm going to distribute this negative through. I end up with the 2x plus 1 can stay 2x plus 1 minus x squared. Distributing the negative times the positive makes this minus 1. This is all dx. That's equal to the integral. Again, I'm not integrating yet, just simplifying the inside. 0 to 2. The integral from 0 to 2 of here, this inside of the integral, right, the integrand becomes you can say it as 2x minus x squared, or you could write it as negative x squared plus 2. It doesn't really matter. I'll write it as 2x minus x squared. The positive one and the negative one cancel. dx. And then you're ready to integrate this. To integrate, what's the integral of 2x? Well, it's 2x, remember add 1 to the power, divide by that same new power. And you might be able to tell that these 2's are going to cancel. It's just going to be x squared immediately, and that's okay if you do. What's the integral of x squared? Well, it's x to the third divided by 3, because you add 1, divide by that same new power. And we're evaluating this from 0 to 2. And then these 2's cancel, and we'll substitute in. Alright, so if I substitute into here, I end up with substituting in 2 first, right? I would have 2 squared minus 2 to the third over 3. Minus substituting in 0, I'd have 0 squared minus 0 to the third over 3. Make sure you have parentheses around this because that negative would have to be distributed through. In our case, though, this 0 squared minus 0 to the third is all going to be 0. So that goes to 0. Make sure you always check that. It doesn't always go to 0, but in this case it does. And you're left with, we've got 2 squared, which is 4, minus 2 to the third, which is 8 over 3. So 4 minus 8 thirds, you want a common denominator here. 4 is how many thirds? Well, 4 over 1 is the same as 12 over 3 minus the 8 thirds. And 12 thirds minus 8 thirds will give us 4 thirds. Remember, this is area that we're finding, so it's 4 thirds units squared, or you could say square units. Make sure it's one or the other. Leaving it improper is fine. If you said 1 1/3 units squared or 1 1/3 square units, that'd be fine too. But that's the area bounded by these two curves. Bounded means, you know, the curve intersects on both ends of this, and it's what's in between them. It's always the integral of the top minus the bottom curve. If you didn't do this in the correct order, top minus bottom, you might get a negative value, and that would give you a negative area, which, remember, area is always positive. So that's important. And you can't just change the sign at the end. I want to see the correct work that's involved there. All right, let's take a look at one more like this. If I said to find the area bounded by the graphs of y equals x squared minus 6x and y equals negative x. And again, you might want to look at the shapes of these graphs. Just, you know, intuitively, y equals x squared minus 6x is going to be a parabola type shape. Y equals negative x, that's a line. It has a slope of -1, and you know it goes through the origin because the y-intercept is 0. To find the intersection points, right, for my solution, just like I did in the last one, remember how we do it. To find the intersection points, you want to set the functions equal. So I'm going to set x squared minus 6x equals to negative x. And in doing that, I'll add x to each side to get one side equal to 0. So I have x squared minus 6x plus x makes this minus 5x equals 0. Watch your signs on that. And then when I have x squared minus 5x equals 0, we solve this by factoring. So I'll factor out x, end up with x minus 5. So x times x minus 5 equals 0. This gives us two answers, right? We get x equals 0 and x minus 5 equals 0. Adding 5 to each side of that, we get x equals 5. Remember, these are the x values. We're going to find the y values that go with them. To find the y values, we substitute into either of the original functions. It's probably easiest to substitute into the y equals negative x. So for 0, we'd have y equals negative 0, which just equals 0. So one point where they cross is 0, 0, the origin. Another point where they cross, y equals negative x was 5, so then y equals negative 5. So this would be the point 5, negative 5. So this is where these two graphs intersect. Let's draw ourselves a small sketch just to kind of understand where they intersect. You know, if this is the x-axis and this is the y-axis. I'm just going to do a rough sketch. It doesn't have to be 100% accurate. At least you have an idea of what you're looking at here. We know that we have the line y equals negative x. We know that they have intersection points at 0, 0, and 5, negative 5. So it's probably easier to just draw the line y equals negative x first. So y equals negative x. You know, we know we have 0, 0, and then you could go down 1 over 1, down 1 over 1, but we know we're at 0, 0, and then we know we're also at the point 5, 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5. So at 5, negative 5, right, what I'm looking at here is that's where the line goes through. Alright, so this is y equals negative x. And then the parabola, alright, so we've got 0, 0, and then if you kept going down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1, you get to that point. So this is the point 0, 0, this is the point 5, negative 5. If I wanted to draw the first function, the y equals x squared minus 6x, I know it's a parabola, I know it opens upward, and since it has to go through these 2 points, I really have a very good idea of what this should look like. It should be a parabola that's opening upward and going through these values, so it has to go kind of like this. Remember, this is a sketch. I didn't find the vertex, I didn't find the x-intercepts or anything like that. But I know if this parabola opens upward, which I know it does because the coefficient of x squared is positive, then it has to go through these 2 points. It has to kind of have a parabola type shape like that. And remember, we're doing this just to get the idea of which curve is on top and which is on the bottom. So if I have y equals x squared minus 6x, right, you can find the area of that space in there. Well, how do we do that? Well, we take the integral. Remember how the integral works, right? The top curve is actually the green curve here. The bottom curve is the red curve. It's how the area is being bound. So we want the integral from what to what? Well, the x values go from 0 to 5 of the top curve, which is the green curve, which would be the y equals negative x. So of negative x minus the bottom curve is the one in red, which is the x squared minus 6x. Make sure you put parentheses around it because you're subtracting that whole second function away from it. And this is with respect to x. Remember, we're talking top curve minus the bottom curve. That's how you know. The sketch is here just to help us. The sketch isn't necessarily part of the problem, but it gives you an idea of which curve is on top and which is on the bottom. Once you have that, you're ready to simplify and then integrate. So if I simplify this integral at 0 to 5, this will be negative x, distributing the negative through, minus x squared, and then negative times that makes it a plus 6x dx. And then that integral is actually equal to, right, the integral from 0 to 5, simplifying this, we have negative x plus 6x, so I'll write this as negative x squared. Negative x plus 6x would give us a positive 5x dx. And then we want to integrate. To integrate this, negative x squared, remember this will be a negative x to the third over 3. Remember, you're just adding 1 to the power divided by that same new power. The negative stays in front as a coefficient. Plus 5, this will be x, add 1 to the power, so it becomes 2 divided by 2 because that was x to the power of 1. And we're evaluating this from 0 to 5. Remember how you evaluate your definite integrals. You substitute in the upper limit first, so this would be negative. And remember, this negative is out in front of this, so it's negative 5 cubed. The negative isn't getting cubed, just the 5 over 3 plus 5 times x squared, which would be 5 squared over 2. Alright, and that's me substituting in 5 first, minus, and then we want to substitute in 0 While substituting in 0, we have negative and then 0 cubed over 3 plus 5 times 0 squared over 2. And then we're going to evaluate. Well, this left, or this right part, 0 to the third is 0, 5 times 0 is 0. This is all 0. So I'm left with here, simplifying this, negative 5 cubed is 125 over 3. Plus here, 5 squared is 25 times 5. Well, that's actually plus 125 over 2. And getting a common denominator here, the common denominator would be 6. So we have to multiply the first fraction in the numerator denominator by 2 to make this over 6. So 3 times 2 got me 6. So 125 times 2 would be, this would be negative 250 over 6. Plus, to get the common denominator 6 over here, you'd multiply 2 times 3 to get 6. So 125 times 3 is 375 over 6. And then you've got negative 250 over 6 plus 375 over 6. This ends up equaling 125 over 6. And this is units squared or square units. Your choice on how you want to just explain that or use those units. The important thing though is that you're talking about the units. You know that we're talking about a value that came out positive. Its area, it should come out positive. If the area didn't come out positive, that means you made an error somewhere. Typically, people make errors in here, the top curve minus the bottom curve. If you don't put that in the correct order, I can't give you full credit. You can't just change your answer at the end to be positive just because you know it has to be. All right. We will do the next examples for this section in a separate video where we talk about the average value of a function.